Okay, numbers 4. Let's start with 4. Maybe we do 4, 5, and 6 in this video. So this is a mass is suspended from the roof of an elevator by means of a spring balance. So let's say there's a mass. Spring balance is just it's like a scale that hangs upside down. It's a spring scale. So we can call it tension, or we can just say the force of the scale acting up. The elevator is moving upwards, and the reading on the scale is noted in 3 different things that the elevator is doing. The elevator is it's moving upward, by the way, so speeding up, constant speed, and slowing down. So first of all, we know that Newton's second law says the sum of the forces equal ma. So when A equals 0, sum of the forces have to equal 0. That's really Newton's first law, that forces have to be balanced on an object that is not accelerating. So let's look at it 3 ways, really. So we can do a little free body diagram for each one. Moving at a constant speed, right? mg would equal this reading on the scale. When the object is speeding up while moving up, little quick review, this quarterly will have some kinematics. Moving up and speeding up, right? That's positive acceleration. So Newton's second law says positive acceleration means that the reading on the scale must be bigger than the weight. Calling that RU for whatever reason. And then slowing down. So moving up and then slowing down. So I'm going to label this one RU, and this one was called RD. Slowing down. That's a negative acceleration. So that means I haven't been paying attention, but my weight vectors should all be the same length. Looks like they got a little longer, but the important thing is that we show that the vector, the reading on the scale now, has to be less when it's slowing down. So remember what we're saying, sum of the forces have to equal mass times acceleration. So sum of the forces, and I don't need to write 3 equations, it's the same equation every time. The force, the scale is pulling up, the earth is pulling down, and together those have to equal the mass times the acceleration of that system. For the second one, if the acceleration is equal to 0, right, put a 0 in for A, and I know the scale has to be the same as mg. For the first one, if the acceleration is positive, then the only way that this comes out to be positive is if the scale reading is greater than mg. If that was you in the elevator, that's when you feel a little bit heavy because the elevator accelerating upward needs a larger upward force. For the last one, right, if the acceleration is, for this one, is negative, then the weight has to be greater than the scale reading in order for the value on the right for acceleration to be negative. The weight has to be larger. The negative value has to be larger. So which of the following is a correct relationship between the readings? Well, we can clearly see that the biggest reading has to be speeding up. The smallest reading has to be slowing down, and then the constant speed will be in the middle. So I'm not sure which answer that's going to come out to be. RU has to be greater than RC. Well, that's true. RU has to equal RD. Well, that doesn't make any sense. RC equals RD. No. RC is less than RD. No. And RU is less than RD. No, right? So A, we could have a lot of combinations of things that could be correct. I just wanted to check them. So the reading on the scale up has to be greater than the reading when it's a constant speed, and that makes sense. Look at what Newton's law says. The reading on the scale equals the weight at constant speed. The reading on the scale has to be greater than the weight when we have a positive acceleration. A student weighing 500 newtons stands on a scale. When a scale reads 520, the elevator must be doing what? So this is the same problem. Let's diagram this out. Here's my student, right? So that student weighs something, whatever that is, and that student is standing on a bathroom scale, and we know that the bathroom scale is what we typically experience as the normal force, right? A scale just quantifies that. We can look at a scale and it tells us what the normal force is. So let's write an equation for that. Sum of the forces equal mass times acceleration. So the scale minus the weight equals ma. Okay, so the question says a student weighing 500 newtons stands on a bathroom scale in an elevator when the scale reads 520. So that means 520 newtons minus 500 newtons equals, what's the mass, right? If weight is equal to mg, and again, that's just another version of F equals ma for a free-falling object, then the mass has to equal 500 over 10. So this is a 50 kilogram student, right? Be careful with weight and mass. They're not the same thing. Equals 50 A. So I have 20 newtons of net force, and that really answers the question. If there's more upward force than there is downward force, then the object must be accelerating upward. I actually have enough information here to solve that. 20 newtons of net force over 50 kilograms of mass equals 0.4 meters per second squared. Positive, right? It's a positive value, so accelerating upward. Number 6, a box slides to the right, and when you're reading these, you should be diagramming them as you go, or read it first. Box slides to the right across the floor. Person called Ted exerts a force T to the right on the box. That's the Ted force, I guess. Person called Mario exerts a force to the left, which is half as large as T. Given that there is friction and the box accelerates to the right, rank the sizes of these three forces. This is a good one. So let's diagram it first, right? So I have Ted to the right, call it a T. We have Mario to the left, that's half as large. And it says, given that there is friction and the box accelerates to the right, so if the box accelerates to the right, then that means I have to assume that friction then is also to the left. And we're going to rank these. So we can write an equation first. Sum of the forces equals mass times acceleration. So drag and drop. T positive minus m, which is negative, minus f, which is negative, equals m. And again, that's not Mario. That's the mass times acceleration. So this is kind of a neat problem because you really have, there's some logic here, right? So on a basic level, if the box is going to accelerate to the right, then T, we know, has to be greater than m plus f, right? Because the only way this box accelerates to the right is if there is more force to the right than to the left. So we know that has to be true, but that's not going to truly answer the question. It can eliminate some stuff, right? We can see, probably looking through here, that some things cannot be true. T can't be less than F. That doesn't make any sense, for example. But let's now read between the lines and look at the details. It says that M is half. So M is the same as T over 2, right? So if M is equal to T over 2 and F is greater than M, then that doesn't make sense. If F is greater than T over 2 and M is T over 2, then we'd have a net force to the left. So that can't be true. If F is equal to M and M is T over 2, then the total force to the left would be equal to T, and that says the forces are balanced. That couldn't be true. So that means that M must be greater than F, right? So T must be greater than both M and F combined, and M must be greater than F. So we must have something in our choices that tells us that T has to be greater than M, which has to be greater than F. And I can see it right there as letter A.